Okay, hello everyone, and today we're looking at exercise 5.6, which is projectiles launched obliquely. Before we go any further, oblique means to be launched at an angle. Okay, so instead of being launched straight horizontally or straight vertically, it is an object being launched at an angle. Okay, so a quick reminder from 5.5 stuff. Okay, a projectile for this exercise is at this level, at year 12 level. A projectile is a body that's been thrown or projected and is traveling freely through the air. While undergoing projectile motion, the object is under the constant, unbalanced force of gravity. Okay, so there is a net force acting on the object. That net force is gravity. Okay. Therefore, if we have a net force that is not zero, we have an acceleration, yes? Now, some common assumptions for this projectile motion. No consideration is given to the force projecting the body or what happens to it when it lands, okay? So we care from right after it's released from its launch mechanism up until right before it hits the ground. Okay? We don't care how it's launched, is it a spring, blah, blah, blah. We don't care about any of that. We're caring about once it's in the air, then we can start using these equations of motions we're going to make. We are also, air resistance is considered to be negligible, okay, in quantitative questions. So any questions to do with numbers, okay, we're going to ignore air resistance, okay. Some questions, when they're asking about qualitative answers, like how just worded answers, okay, rather than a numerical solution, that may include, okay, air resistance. So you need to think qualitatively about that and what impact air resistance has. So which direction that applies a force, which creates a net acceleration, how that impacts your question, okay. But horizontal versus vertical versus horizontal acceleration. This is the same image from 5.5, but we're going to go over it again. Okay, so the big thing to point out here is as we go from here to here, okay, and if we went some time interval back from here to here, that distance x is going to be the same for every delta t. Okay, we might think of 0.1 of a second, 0.1 of a second. The distance it travels there and the distance it travels there is the same because, okay, in the horizontal, there is no acceleration. Okay, so if there's no acceleration, that means the horizontal velocity is constant. Whatever it is when it first gets launched, whatever the horizontal component is, it remains the same all the way throughout. If it gets launched with a 2 meters per second horizontal component, it has a 2 meters per second horizontal component throughout its whole flight. So the displacement it covers horizontally is quite easy. It's just that horizontal component times by the time in flight. That is really, really easy. That's how you find the horizontal distance displaced. Now, vertical is a little bit different, okay? Because for vertical, okay, we have a net force, okay? That force being gravity. Okay, so if we have a net force, we have a force that does not equal zero. Okay, so we have a force, that means we get an acceleration, and that acceleration is g. Now, if we substitute that a value, okay, we substitute that a value into our v equals u plus at, we get this lovely equation here, okay, which tells us the velocity vertical component at any point in time. Okay, you need the initial vertical component, and then after a given time and gravity, okay, we'll get our vertical velocity at that point in time. Okay? Same with displacement, we can calculate using our initial vertical component and then gravity impact. Now, these equations are written, that's a plus there because it is plus at. Okay? You need to be really careful with these two equations which direction you take positive. Okay? Because most of the time you're going to be dealing with something launched like this. Okay? And on the next slide you'll see we can break this initial component down into a horizontal and a vertical. Okay? This vertical here, this u vert, okay, initial component, that is in the opposite direction to what gravity is acting. Okay, so you need to pick one of these two as positive. I would normally pick the initial velocity positive and gravity as negative. Okay, so when you're substituting into this, you need to make sure, okay, G isn't just 9.8, G is negative 9.8 in this situation over here, because we've declared that up is positive. That means the gravity, the force of gravity, is acting downwards. That's a negative direction, so G is negative 9.8. So when you go and substitute it into this, we get V vert equals U vert minus 9.8 T. Okay? So you've got to be really careful with your signs. Some people cheat and put this as a negative straight up, okay? But that is technically incorrect, okay? You need to decide which direction is positive and then make sure you put the correct values in your equation, correct signs. Okay, so our total, if we want to calculate the total velocity at any one time, is we add the vertical component and the horizontal component using vectors. Okay, you add those together, so you want to find it at this point here. Okay, we find the vertical component, we find the horizontal component, add those two together. That gives us our resulting velocity vector. Okay, so let's go through a full example. Okay, so we're launching some object. Okay, could be a baseball, basketball, whatever it is, some object. Okay, at some initial velocity. Okay, v0. Okay, also u. Okay, we can use either one. Okay, u or v0. Okay, at some angle theta. That's what we're going to do, and we know it's going to follow this path. From observing everything we've ever seen in the world, it follows this path. So, v0 represents the initial velocity and can be resolved into two components. We can break it down, okay, into a horizontal and a vertical component. And this is a picture showing here. Now, using trigonometry, okay, just using SOHCAHTOA, okay, sine equals opposite over hypotenuse, cos equals adjacent over hypotenuse, we can resolve it into these two components. Okay, so if we have some v0, good. Do my dash down here and do u vert over here as well. Okay, we've just got a right angle triangle. Okay, v0 is our hypotenuse, some angle theta. We can resolve it to find our initial vert and our initial horizontal, where horizontal is initial velocity cos theta, while vertical is initial velocity sine theta. Now you can remember those two formulas, or you can always make them yourself. You literally just draw right angle triangle, okay, UH, UV, and figure it out. Okay, that's year 9 maths. Quite easy to do. Okay, so you can either remember or you can always resolve it yourself. Okay, so taking what we had before, okay, on the previous slide, okay, we're going to now transfer these, okay, to take into account our initial condition, okay, this over here. So our acceleration horizontal is still 0, okay. Our horizontal velocity is our horizontal component. We said that before. Now our horizontal component we now know is v0 cos theta. Have that down there, and we can substitute that in and get our displacement at any time. Okay, our displacement is equal to velocity times time, because there's no acceleration in the horizontal, and our velocity in the horizontal is v0 cos theta. Okay, now with the vertical, okay, and this is where, and I haven't changed this slide. That is a positive. That is a positive. Okay. We're taking up as positive. Velocity is changing because in the vertical we talked about again, we have gravity affecting. Gravity, that means we have an acceleration of g, okay, which is negative 9.8. Yeah, okay, so our velocity is v equals u plus at. Well, u, our initial velocity in the vertical component, is that. Okay, and we're going to take, sorry, you can hear my dog running around. We're going to take up as positive. Up as positive. Okay, so our initial velocity is v0 sine theta in the vertical component. Okay, and then plus acceleration times time. So our acceleration in this case is purely due to gravity because we're ignoring air resistance. Okay, so gt. Now, in this case, we said positive is up. That means g equals negative 9.8. Okay, so you'd put negative 9.8 in there. Okay, but to be technically correct, these should be positive signs, and then g is negative 9.8. Our displacement, same thing. This is using that ut plus half at squared, okay, because our acceleration is constant. So in there we put g, which is negative 9.8, and our initial, okay, is our initial in the vertical component. So we can now, we may as well write this in full. We get v0 sine theta t plus half g t squared. Okay, and big thing, I know I keep harping on about it, but it's to be correct because it's very common. 9.8, negative 9.8, g is negative 9.8 because we've taken it up as positive. Okay. And just like before, if we want to find the velocity at some point here, okay, we find the horizontal, sorry, we find the vertical, we find the horizontal component, and we can add them together as vectors. Okay. So that's breaking down. The big thing is we turn this problem into two separate parts. Whenever we're launched obliquely, we turn it into two separate parts. We turn it into horizontal motion and vertical component motion. Okay. Keep them separated until we need to add them back together for some form of total sometime later. Okay. So let's do some example problems. An object is fired from a point P and follows a parabolic path. Okay, so that's parabolic, looks like that. Okay, so we've got some oblique launch, reaching its maximum height at Q. Okay, so its maximum height there is Q, and returns to the same level as point P. So it's launched from point P, okay, at point R. Okay, so launch from P, goes through max height at Q, back to R. Air resistance is negligible. Okay, which of the above statements are true? Okay. Which of these three statements are true? The time from P to Q is greater than the time from Q to R. Okay, so P to Q, Q to R. Does it take longer to get up to Q than it does to go from Q back down to R? Well, ignoring air resistance, okay, it's the same distance up as the same distance down. Okay, and it's the same distance across. Okay, and our horizontal velocity does not change. Okay, we have the same acceleration acting as we're trying to go up. Have zero vertical velocity when we're at the top, and then we're coming back down. So this is false. Okay, it doesn't take longer to get up than it does to come down when air resistance is negligible. It takes the same time. Its speed at P is the same at R. Okay, well, one thing to notice, it says speed, not velocity, but that's just its total velocity at that point. Well, that is going to be the same. The velocity here, or the speed, okay, okay, because we're doing speed, so just the magnitude of the velocity, the magnitude, even though this is going up and this is coming down, the magnitude of them is going to be the same. Okay. Because if we thought of the thing that just goes straight up, comes back down, okay, as it goes up, okay, it has, let's say it starts at 10 meters per second, goes up at the top, it's at 0 meters per second, okay, and then comes back down, it's at 10. Okay. The exact same thing is when it's like this, is just there is an added in horizontal component that this might be the velocity horizontal is 3 all the way across. It's still the vertical component would still be 10 up to 0 and 10 for the vertical components, okay? And the horizontal is constant. You add that in as a vector. Okay? So you could do some vector addition. But what what this is noting is when we discount air resistance, the at the same height, okay, the launch and finish, if they're at the same height, the velocity magnitude will be the same. So that is true. The acceleration at Q is 0. Okay, so up here it's saying the acceleration at Q is 0. That is false. That is false because gravity is acting on this object at all times. Here, all the way along, gravity is still acting on it at all times. So that is false. So only statement 2 is the only statement that is true. So let's do some maths. In a shot put event, a 2 kilo shot is launched from a height of 1.5 meters with an initial velocity of 0.8 meters per second and an angle of 60 degrees to the horizontal. Answer the questions below about the motion of shot put. Okay, so let's put this in. We have m equals 2. Okay, our initial height is 1.5. V naught, our initial velocity, is 8 meters per second, and our theta is 60 degrees. Okay, let's draw a picture. We should always draw a picture first, so we're clear on what's happening. Okay, we have ground level. It is being launched, okay, at a height of 1.5 meters. Looks something like that. Not the best parabola I've done in my time, but it is. Okay. And that angle there is 60 degrees. Ooh, let's just go with it for now. Not the best, but. And that is second. Okay. That's what's happening in this case. Okay. Question A, what is the horizontal speed of the shot? Okay, or it wants to know what is the horizontal component. Okay. So we need to find the velocity horizontal. And if we remember back from our slides on the previous, okay, back here, it is V naught cos theta. V naught cos theta. Okay. So it's a simple substitution. 8 cos 60 equals 60. I'm just doing this on my calculator. That gives me 4.0 second. Okay, and I put the 0.0 because we were given 2 significant figures here, 2 significant figures here, 2 significant figures here, 2 significant figures here. So that means all our answers should have 2 significant. Okay. What is the initial vertical speed of the shot? Well, just like the horizontal, we have our equation. It is equal to V naught sine theta, 8 sine 60, and that is going to give us, that gives us 6.928. Okay, 6.928, so 6.93. Oh, no, we don't need the 3. 6.9 meters per second. Okay, that is the initial horizontal speed. Okay, the initial vertical horizontal speed. Of course, as it goes up, gravity is pulling it down, so the horizontal will reduce. How long does it take the shot to reach its maximum height? Okay. Well, let's have a think about this. Okay. Let's have a think about this. When it gets to its maximum height, up here, okay, see, at maximum height, its vertical, its velocity, there, is equal to 0. Okay, it's not traveling up, nor is it traveling down. At that perfect point in time, its vertical velocity is 0. Okay, we know A acting on it is 9.8. T is our question mark. Okay. Now we could write our initial vertical velocity, 6.9. So we have, oh my God, I can't write today, sorry. We have 4 known, or 3 known values and 1 unknown time. So there is a equation that we can use to find this, one of our motion of equation, because our acceleration is constant. And so we can use v equals u plus at. Okay, our final velocity at the top is 0. Our initial velocity was 6.9 minus acceleration's down because we've decided up is going to be positive, minus 9.8 t. So we solve this, we are going to get t is equal to 6.9 on 9.8. So the time to get to the top, 6.98 is 0.704. So 0.7 seconds. D. What is the maximum height from the ground that is reached by the shot? Okay, well, we need to find this distance height here and then add the 1.5 because it's being launched from 1.5 meters above the ground. So same thing. Okay, we have a displacement now. Our initial vertical velocity, we know 6.9. At the highest point, its final vertical velocity is 0. Our A is negative 9.8. Okay, we know our T is now 0.7 seconds. So we can use this displacement equation just here, ut plus half at squared. Okay, so x equals ut plus half at squared, okay, or x is equal to the initial velocity by time plus half g times squared. Okay, so let's substitute all this in. We get 6.9 by 0.7 plus half by negative 9.8 and by 0.7 squared. So I've run out of space here at the side. Okay. Stick that all in our calculator. 6.9 by 7 plus times by 8, and make sure you put your 9.8 as negative. Okay, is 2.429. 2.42 meters. Okay, so x total is equal to 1.5 plus 2.4 is equal to 3.9 meters. So at its highest point, it is 3.9 meters above the ground. And lastly, part E, what is the speed of the shot when it reaches its maximum height? Okay, so here at this maximum point, let's think of the two components, okay, because we want the total. What is the speed? It's not saying horizontal or vertical, we want the total, okay? So total is equal, and this is vector addition, equal to the horizontal plus the vertical. Now at the top, at this very top point here, this vertical bit is 0. So our total speed at the very top is just our horizontal component. So our total speed, we set our horizontal component up back in part A is 4 meters per second. So that's how we do that problem. Okay. Example 3, a projectile is fired at an angle of 30 degrees to the horizontal, playing with an initial velocity in the same direction of 60 meters per second. The total time of flight for the projectile is closest to what? Okay, so we have theta equals 30. We have v naught of 60 meters per second. Okay, that's what we're given. We know g is equal to negative 9.8. So let's draw a picture. It goes up like that. Angle there is equal to 60. Initial v naught is equal to 60. And we want to know time in flight. Okay. Bunch of ways we can go about this. All the ways we go about this, though, we at least need to know the initial vertical velocity. Okay. And initial vertical is v naught sine theta. Okay. So you get 60 sine 30. 60 sine 30 is 30. So its initial vertical velocity, the vertical component, is 30 meters per second. So there's a bunch of ways we can do this. One way is to calculate the time it takes to just get to the top. Okay, because the time it takes to the top is exactly the same as the time it takes to get to the bottom, so we could just double that. Okay, so we could find the time to there and then double, and that gives us our total time. Okay, we could say, when we consider just the vertical, we could draw it just like this because we're ignoring the horizontal. Okay, it's just like that. Okay, its initial position x equals 0, its final position is x equals 0. We could substitute that into x equals ut plus half at squared. Okay, we could put 0 in there because technically its position, its displacement, once it gets to the end, is 0. Okay, and that's going to leave us with a quadratic though for t, so you're going to have to solve a quadratic. You'll get two values for t. One will be 0, okay, because at time equals 0, it's at the starting point, and then the other t value will give the final point, but that requires solving quadratic, which isn't very good, especially if you're under pump and it's a calculator free. Just avoid having to solve quadratics. Maybe these are nice. It could be worse. Yeah. They're the two main ways you could do it. You could do it a couple other ways using the other equations. You can always use the other equations in some way, shape, or form. I suggest let's go from the initial point up to halfway. Okay, because at that point we have the initial velocity we found to be 30. Our final velocity is 0 in the vertical component at the top. T equals question mark. And a equals negative 9.8. Okay, so we can just use E equals U plus AT. Okay. 0 equals 30 plus negative 9.8 because up positive T. So T is going to be equal to 30 on 9.8. Okay, 3.06. So we had two significant figures. So we're going to say that is 3.1. Okay, so we times by 2, so total time is equal to 6.2 seconds. Okay. So closest to will be B. The big thing for these, when we get to ignore air resistance, the time taken to get to the top is the same. We can double that to get back to the same height as initial position. Okay, up to there is the same at the height as initial position. Now, if you kept coming down, like in our previous example, okay, the shot put that started 1.5 higher, Okay, if we kept coming back down, well, the time from there to there is different from there to there because the vertical displacement is different. Okay. So quick summary. Draw fully labeled diagrams. Always draw fully labeled diagrams. Once we have that, we can treat the motion as two separate motions, two separate problems. Okay, the horizontal velocity is constant. Okay, v0 cos theta. Okay, and the vertical is changing with an acceleration of negative g because we generally let up to be positive. Okay, and our vertical velocity, vertical initial is v0 sine theta. Okay, that's the initial at a u. Okay. List the data under vertical and horizontal. So what you could do, okay, over here we were just dealing with vertical, but you can make a little table. You could say horo and vertical, okay, and in this case, horizontal would be initial horizontal is equal to, would that be 60 cos 30. So that'll be whatever it is. We know our initial vertical is 30, okay, and you could start listing all your values in separate sides, horizontal or vertical, depending on what you're dealing with. Okay, so that's what that one's saying. Vertical motion, we get to use v squared equals u squared plus 2ax, or v equals u plus at, or we also get to use, that has come across, we get to also use x equals ut plus half at squared. X equals t plus half at squared. That's another really handy one. Okay, usually you're going to be given information about one direction, asked to find something else about the other. You go from one direction to another, that you find the common link is time of flight. Remember, it takes the same time to go up as it comes down to the same height. Okay, we can split that in half. Those two halves are exactly the same. Okay, label the direction plus or minus for all variables except time. Okay, so in this case, the vertical component there, that would be positive, but the vertical component there would be negative. So you've got to be really careful with that. And that's it for 5.6. If you have any questions, stick them up.